In this video, we will look at an example of a synchronous sequential circuit where we create a simple counter. In this example, what we are going to see is a simple counter. You'll notice we're counting with 2 bits from 0, 0 to 0, 1 to 1, 0 to 1, 1. Or in decimal it would be from 0 to 1 to 2 to 3. The arrow that loops back into the same state in each case is marked with a 0. In other words, if our external input is 0, then we'll stay in the current state. We'll see that the lines connecting one state to the next are marked with a 1. If our external input is a 1, we will advance to the next state. Here in the state table, you see the same information as there was in the state diagram. We see the 4 states that we have right now. A and B will spell out 0, 0, 0, 1, 1, 0, 1, 1. The next state, if x is 1, will be the same as we had before. It won't change. However, if x is 1, we'll go from 0, 0 to 0, 1. From 0, 1 to 1, 0, from 1, 0 to 1, 1, and from 1, 1 back to 0, 0. We now will start putting together the excitation table. We'll have the present state and the external input together. These are, in effect, the inputs that we have, and you'll see all 8 minterms. The first thing that we need to do is to determine what the next state is for each of these minterms. You'll see here that the 4 minterms where x is 0 are noted by x being larger and in red. And you'll notice next to it that A and B have the same values as they did in the present state. That's because since x indicates that we are not incrementing the counter, we want to be clear and explicit that we are leaving these 4 alone. You'll see here that it is the 4 cases where x is 1, where the x value is in red and larger. These are the 4 cases where we are incrementing and going to the next state, where we go from 0, 0 to 0, 1, from 0, 1 to 1, 0, from 1, 0 to 1, 1, and from 1, 1 back to 0, 0. Here you'll see that we compare the present value of A to the next value of A when we have A and B together as 0 and x is 0 as well. Going from 0 to 0 means we're leaving it alone. As you go back to the excitation table for a JK flip-flop, this will work if J is 0 and K can be either 0 or 1. And that's how we mark it here. Although we're pointing specifically to A, it's a similar situation for B, where it's going from 0 and remaining 0. So JB is 0 and KB can be either 1 or 0. In both cases, it being able to be 1 or 0 means that we place an X there because these are don't care conditions. In this case, A remains the same as it was before. It goes from 0 to 0. So we see that JA and KA again will be 0 and a don't care condition respectively. But what's different here is that B is changing from 0 to 1. And if we look at the excitation table for JK flip-flops, we know that in that case, JB will be 1 and KB will be a don't care. Here we see A will remain 0 as the input is 0. B will also remain the same value, but the value this time it's remaining is 1. As before, the JK flip-flop for A will be 0 for J and don't care for K. However, for B, J is going to be the don't care this time, and K will be 0. As we move one more row down, again, we're starting with A and B being 0, 1, but the input is 1. This will lead us to have A is 1 and B is 0. A going from 0 to 1 we have seen before, and that'll mean that for the A flip-flop, J is 1 and K is a don't care condition. But for the other one, if we go again to the excitation table for JK flip-flops, we'll see that as the value goes from 1 to 0, J is a don't care and K is 1. With X equal to 0, we remain in the state 1, 0, with A going from 1 to 1 and B going from 0 to 0. Going from 1 to 1, we have A's flip-flop with J as a don't care, K at 0, and for B's flip-flop, B going from 0 to 0, JB being 0 and KB being a don't care. Here, A is 1 and B is 0, going to A is 1 and B is 1. A remaining the same at 1, the A flip-flop has a don't care for J and 0 for K. On the other hand, B is going from 0 to 1, so its J input is 1 and its K input is a don't care condition. In this state, A and B both remain at 1. So in both cases, J is a don't care condition and K is 0. Here, in the last situation, we have the present state as A and B both being 1, and with an input of 1, the next state is going to be both of them being 0. Since they are both going from 1 to 0, in both cases, the J input for both flip-flops will be a don't care condition. The K input for both flip-flops will be 1. And here you can see the completed excitation table. If you look, you'll see that the variables that we are looking to determine values for in terms of the present state of A and B and the external input of X is going to be JA, KA, JB, and KB. In all four cases, we have 4 don't care conditions. In the case of A, we have one instance for both J and K, where they will be 1. And in the case of JB and KB, 2 instances where they will be 1. Here we have a block diagram for the sequential circuit. We have an external input X, and we have 4 internal inputs, A and A prime, B and B prime. Coming out of the combinational circuit, we have going into the flip-flops, JA and KA, the J and K inputs for flip-flop A, JB and KB, the control inputs into flip-flop B. What we need to find is how A prime, B prime, and X will determine the values for J and K going into both flip-flops. As we can see on the excitation table, there are 4 cases of don't care conditions for JA, where A is 1, B is 0, and X is 0, where they are 1, 0, 1, 1, 1, 0, and 1, 1, 1. There is exactly one case where JA is 1, and that is where A is 0, B and X are both 1. Here we see the Carnot map for JA as a function of A and B at time t and X. From this we can tell that what we need to put into JA is the value of B at time t ANDed with X. Here we see that the one place where KA is 1 is for A and B both being 1 and X being 1. All 4 cases where A is 0 are the don't care conditions here. In the Carnot map for KA, we see that KA will equal B at time t ANDed with X, the same thing as we had for JA, coincidentally. Here we see two cases where JB is 1, where A and B are both 0 and X is 1, and where A is 1, B is 0, and X is 1. Additionally, we see that there are 4 don't care conditions, all in cases where B is 1. Here we see from the Carnot map that in this case JB is X. For KB, we see that, again, there are 2 places where it is set equal to 1. When A is 0, B and X are both 1, and where A, B, and X are all 1. The don't care conditions here are specifically where B is 0. And in the Carnot map for KB, we see again that KB will equal X. Here we see the final circuit. X goes into J, but before that happens, it splits off twice. One to go into an AND gate that B also goes into, and secondly, it goes into KB. The result of the AND gate, which has BX, will go into both J and K for flip-flop A. And this is the completed circuit.